Hey everyone, and welcome to this explainer. I am absolutely thrilled to share this with you today because honestly, we're looking at one of the most bizarre and fascinating structural routing mysteries in AI right now. So, if you're working with multimodal large language models, or MLLMs, you know that injecting or correcting entity-specific facts is a huge priority. We all want a lightweight alternative to full fine-tuning, right? Well, a groundbreaking new archive paper, specifically 2606.17057, reveals a completely silent failure that's happening right under our noses in production systems. Today, we're going to unpack exactly what's going wrong with knowledge editing, and more importantly, how a brilliant new method called DECODE actually solves it.
The paper's title literally says it all. Correct when paired, wrong when split. And this perfectly encapsulates the core of our mystery. Okay, picture this. You update a fact in your model. You query the model using both text and an image, so a paired input, and it works perfectly. The updated knowledge activates just like you want. But then, you ask the exact same model about the exact same entity using just text, or just the image. Mysteriously, the model just fails. It spits out the old, outdated fact. So why does stripping away one modality suddenly give the model amnesia?
Okay, let's dive into this. Here is our roadmap for today. We're going to unpack the multimodal editing mystery, uncover exactly why unimodal queries are failing, explore the DECODE breakthrough, figure out how this changes your developer workflows, and finally, look at the future of MLLMs. Let's get into it.
All right, Section 1, the multimodal editing mystery and why this is acting as a silent failure in production.
So the researchers have officially termed this whole phenomenon editing decoupling failure. You see, the current paradigm of knowledge editing kind of just assumes that when you update a model's parameters for a specific fact, you're modifying the shared global representation space. But as it turns out, that assumption completely breaks down under real-world queries. Editing decoupling failure is this crazy state where the AI is literally maintaining two parallel knowledge states, depending entirely on how your prompt is formatted. It's almost like the model develops a split personality depending on whether you show it a picture or just ask it a text question.
Think of it like this. Feed the model a multimodal input, like an image paired with text, and boom, you get the green light. The updated knowledge fires perfectly. But drop the text, or drop the image, suddenly the AI has selective amnesia and serves up the outdated facts. And the craziest part? This isn't some random hallucination or stochastic dropout. It's not a temperature artifact. It is a fundamental structural routing issue. The model is literally treating the multimodal trigger and the unimodal triggers as entirely separate computational paths.
Which brings us right to Section 2, why unimodal queries fail, or as I like to call it, the tale of parallel pathways.
So this brings up a massive question for anyone building or deploying these systems. Where is the knowledge actually stored? I mean, we often visualize a model's knowledge as this big unified database of weights that gets cleanly updated every time we apply a patch. But MLLM architectures absolutely do not store entity knowledge as a single monolithic vector or weight matrix, not even close.
Instead, the paper's empirical analysis proves that entity representations are distributed across disentangled, modality-specific pathways. It's really helpful to think of it like parallel train tracks. You've got your text encoders, your vision encoders, and your cross-modal attention layers. And these maintain completely isolated routing structures. They only actually converge at very specific late-stage decoding steps.
So here is the main culprit. Current editing techniques usually apply gradient-based or heuristic updates to the shared transformer blocks, right, or the cross-modal projection layers. And yeah, those updates successfully bias the model toward the activation pattern triggered by paired inputs. But because the unimodal pathways route through completely different intermediate activations, those edited weights never actually reach the circuits processing the isolated modalities. The updates just completely miss them.
Now you might be sitting there thinking, well, whatever. I always send images and text together, so I'm totally fine. But look at the production systems actually affected by this. RAG systems, document parsers, vision language agents, latency fallbacks. In the real world, developers intentionally strip modalities all the time. We drop images for faster latency, for caching, or for fallback routing. And if your edited model passes your multimodal validation but fails these unimodal fallbacks, you've just introduced wildly inconsistent behavior that your standard evaluation suites won't even catch. It's the exact kind of silent failure that leads to those terrifying 3 a.m. pager alerts.
Okay, Section 3, the DECODE method. This is the breakthrough solution the researchers are proposing to fix this structural routing gap once and for all.
So DECODE is a real game changer because it completely shifts the philosophy of knowledge editing.
Instead of treating the MLLM as a single editing target and just kind of hoping a heuristic weight adjustment trickles down everywhere, DECODE explicitly disentangles and localizes modality-specific neuron groups before applying any updates. It actively isolates the specific computational subgraphs responsible for text processing, image processing, and cross-modal fusion. It's a highly targeted, structured circuit modification.
The DECODE pipeline breaks this whole thing down into 3 distinct phases: pathway mapping, targeted localization, and trigger-agnostic propagation. Let's see how these actually work under the hood.
What's really fascinating here is the sheer surgical precision of it. In Phase 1, pathway mapping, the method identifies exactly which neuron groups activate exclusively under unimodal triggers versus multimodal triggers. And they do this through forward-pass profiling across controlled input variations. Then, in Phase 2, targeted localization, we stop blindly broadcasting updates to shared transformer blocks. Instead, DECODE literally pins the knowledge injection directly to the specific neuron groups that handle that exact target modality.
And finally, Phase 3 brings the whole shebang together with trigger-agnostic propagation. By directly editing those isolated pathways we mapped out earlier, the updated weights become accessible no matter how the query arrives. Text-only prompt? Yup, it works. Image-only input? It works. Paired multimodal sequence? Absolutely works. Extensive experiments in the paper show this consistently achieves effective knowledge updates and completely mitigates that nasty editing decoupling failure.
Now, that is fantastic news for the architecture, but it definitely means we need to change how we work day to day. So, Section 4, updating developer workflows and the new rules for CI/CD.
Listen, because of the decoupling failure, our validation testing simply can no longer rely on just multimodal QA pairs. Engineers have to immediately adjust their evaluation matrices. Your test suites literally must now include text-only entity queries, image-only entity queries, the standard paired ones, and mixed modalities with partial inputs or noise. Because honestly, if you don't explicitly test the isolated paths, you just won't know if they're broken.
Furthermore, the actual editing pipeline itself has to change. Before you apply updates, developers must add a forward-pass profiling step to their CI/CD pipelines. You have to profile the activation routing first. Without that pathway mapping, your edits are just going to continue biasing toward whatever trigger was used during training. Now, I know what you're thinking. Yes, adding a profiling step will absolutely increase edit latency. But actually, it is an absolutely crucial trade-off to prevent silent knowledge drift in your application.
And looking at live production deployments that are serving varied requests, those systems need to implement trigger-aware routing. You really must validate the active knowledge state per request type. Because if you're out there caching edited states without saving the modality context that generated them, you are just going to blindly reproduce the decoupling failure right there in your live environment.
Okay, let's zoom out and look at the big picture in Section 5, the future of MLMs and the move toward trigger-agnostic knowledge.
Now, quick reality check. While DECODE is a massive leap forward, it isn't literal magic. It brilliantly solves the structural routing gap, ensuring that injected knowledge actually reaches the correct computational path. But you still have to do the hard work of basic context management. You still need to rigorously monitor context truncation, token limits, cross-attention saturation, and of course, careful prompt engineering. Those factors will still independently mess with your retrieval accuracy, even if your routing is totally perfect.
Ultimately, though, the big takeaway from this research is super clear. Knowledge editing in MLMs is evolving from a brute force heuristic into a true precision operation. Aligning parameter updates with actual, mapped routing paths, that's the new standard. Trigger-agnostic knowledge injection is rapidly shifting from a bleeding-edge research concept into an absolute baseline requirement for any serious production deployment out there.
So I want to leave you with this somewhat provocative question to chew on regarding your own projects. Is your MLM holding 2 parallel states of truth right now? Seriously, if you haven't tested your multimodal application with isolated unimodal fallbacks, there's a good chance you are serving outdated facts without ever triggering a single error log. I highly recommend checking out the full methodology in the archive preprint to see how you can start mapping these pathways today. Thank you so much for joining me for this explainer, and hey, happy building!